Can you hear me? Good morning, everyone. Welcome to the third day of AICT Atal sponsored online faculty development program on augmented reality and virtual reality, organized by Department of Electrical, Electronics and Communication Engineering, Geetham deemed to be University, Bangalore campus. We are pleased to have Mr. Sai Sri Chaitanya Y to discuss about the topic 3D modeling. Sai Sri Chaitanya Y is a mechanical engineer with an overall experience of 9 years, along with masters in tool engineering. He is currently working with Philips Healthcare as mechanical designer in Pune. Prior to this, he worked with Whirlpool India, Pune, and General Motors TCI Bangalore. At Whirlpool, where he worked with the Global Product Organization for Laundry NPT projects as a lead engineer with the aesthetic team. Sai worked with the manufacturing team at General Motors Bengaluru, wherein he was a part of die engineering team responsible for material stamping, simulation, and die layouts for advanced vehicle development programs. It's my pleasure to invite Sai Sri Chaitanya Y to our FTP program.
Hello everyone. Just let me know if I'm audible.
Yes, sir, you are audible.
Okay, great. And let's see if we can have a
Co-host.
Yeah. Hello everyone. This is Sai here. A mechanical engineer by profession, and yes. So just a second. Some settings are getting updated. Yes. So this. It is an immense opportunity at the same time for me also, especially when they're getting a chance to directly interacting with the faculty members. And so part of the experience what I share. So today's session is particularly on the 3D modeling. So this is the very first time I am also trying to give this on this particular topic. So just going forward, have a thought in mind that the 3D modeling softwares are not, the skill set itself is not defined by the software. Okay, so I had been in industries with automobile, home appliance, and medical healthcare now. So, and I've seen, I was with manufacturing, product development, and now with medical devices. Okay, which is mostly concerned on patient safety aspects as well. So. Well, I'm going to take you forward. It would be appreciated if you can also list on some of your expectations from this session on the chat box. So meanwhile, Mr. Ajay or his team can coordinate the questions accordingly. I have a split screen, so I can also have a timely watch on the chat window if some questions arise. And yes, maybe we can start the session now.
Sure, sir.
I'll start sharing my screen. Okay. Is it visible?
Yes, sir. Yeah.
Okay, great. So introduction to 3D modeling, and I also learned that the audience is a mixture of different disciplines here, not only from engineering, but also from other streams as well. Okay, so I have tried to kept it to the as basic as possible so that it is good. And also I learned that you had a session on augmented reality and virtual reality. So from PTC. So maybe I would like to connect on the same, but it would be a little offset from the previous topics. Huh? Okay, 3D modeling. So what we know is from movies to manufacturing, the 3D modeling is incredibly useful. Huh? So there are hundreds of different 3D programs, of course, and each has a specific application. And 3D modeling allows engineers, designers, craftsmanship, or the entrepreneurs also to flesh out their ideas. So, and before they come out to reality. So what do you see most of the objects around you in this world right now at this generation were first developed in a 3D design by using a 3D software by engineers or some designers. and before they were actually brought onto the into the physical world. Okay, so it is the 3D design is extremely important for the same reason. The engineers, architects, be it a mechanical or a civil or an architect or even industrial designers, and also new and ideas that are getting drastically coming up. So now we know that there is no relation with the degree associated when you want to be innovative. So this is a helpful tool. So there are many, so everyone uses the 3D CAD programs to design things before building them. Okay, so it is being done all the time. So if I go by the basic definition of it, as you can see, it is process of developing a mathematical representation of any surface. Okay, so surfaces can combine to form a volume, they can combine to form a solid, yeah, and which can be inanimate or living, and it can be something that can be visualized in a 3 dimensions. Okay, so yeah, so when I say inanimate or living, so let's say it is something a representation of a tissue or a biological object. It can be a living thing. Inanimate are generally all the physical objects what we see in uh, our consumer items. Okay, so it is important that we understand when we say it is a 3 dimension. Okay, so we have a 3D space. So until the older generation, let's say 2 generations back maybe, we were used to see all the drawings in the form of a 2D space on a paper or something. So slowly we have the 3D modeling has picked up. So so we are able to represent point in spaces using Cartesian coordinate systems. Okay, so and similarly, why I have bought in this mathematical representation is so because during the first terms of the engineering, we used to have this M1, M2, M3, where we used to do a lot of mathematical equations, Laplace transforms, Fourier transforms, something this kind. Let's say at that time I was very let's say a crude level. I was not able to understand what are these being used for in actual application, but the reality is far from that. So what you see, a control point or a control polygon, a complicated 3D surface, what you daily see on automobiles. So it is a math model basically. The 3D software is working using a lot of equations, and maybe a quadratic equation of degree greater than 3, 4 like that. So to give us these physical forms. Okay. And the product that is achieved from this 3D modeling software is a 3D model. Okay. And in general, what we call the person who is working with the 3D models can be referred to as a 3D artist, a 3D modeler, designer, and also a draftsman. Okay. Going next. Yes. So 3D modeling, it can be is traditionally related to the field of engineering, architecture, and making things in general. But we all know that it is also being used in the field of cinematography. Yeah. So artists and designers use this 3D or create these 3D objects, creatures, what you are seeing right now on the screen. So and they also so it is quite in the background you can see an entire world that has been represented in the software. Okay, so these animation softwares are using softwares like Maya, 3ds Max, etc. So today we'll be concentrating on the engineering 3D software. Okay, so, and what are the elements of it, so there are many 3D softwares available in the market. Some of them are listed here. So going forward, we'll also have a demo on Creo because I am working on that. I started my career with Unigraphics, using the tool Unigraphics when I was in GM. Then I also did in Creo. I was in my engineering days. I also took a training on CATIA. In my masters, I used AutoCAD a lot. So all these are just a support for us to make our designs come to life. Okay. So knowing solely the software doesn't serve the purpose. It is also important that we also carry the design or the technical knowledge of what we are going to create. Any questions now before I go forward?
No, Chaitanya, until now.
Okay. Yeah. So this is typically how design takes shape into a product, right? So we imagine that, let's say, for today's generation, when they pick up a component or something, they know that there is something going on by the design. So there are some people who are doing these designs, and there are people who receive these designs in the form of a drawing or some kind of input, and they manufacture it and bring it to the real world. Okay. So what you see in this picture is a let's say a battery holder. Okay. So this was a small project that I was working with some of my colleagues. Okay. So this was a battery holder. So on the top right side, you can see the application of it. So these days, electrical vehicles are in quite popular, right, and getting more popularity. So this is a battery holder that goes inside your electric bike or a scooty. Okay. So there is a stack of cells that is put inside. So what we see is someone made the 3D, and we have an engineering drawing. So I also am saying that. So this is an engineering drawing. So it is considered as a legal document and is still very common in the industry. The 3D softwares are going into a next to a level that they want to eliminate this having a 2D drawing as well. They want to communicate all the technical information on the 3D model itself. So that is something that will take a little time, and these are here to exist because and also when you are entering into contracts with suppliers, and we also want them to suppliers and regulatory boards, we also want them to be on the same path, and this is a good way to sign off our designs. Okay. Yeah. So what I want to represent here is, so there is a big thing that is going from design to product. Okay. And 3D modeling is going to assist a lot during this process. Okay. So you have to interact with the engineering teams within yourself. So may it be a simulation, be it your labs, be it your prototype guys. So, and also cross-function guys. So procurement, manufacturing, quality, and plant, and so on. Okay. So just I'm going to add up. So the next slide could be a bit confusing. Okay. So please bear with me there, because some of you may not have, are still pursuing, may not have an engineering background. Okay. Yeah. This gets interesting here. So what we had as a 3D CAD is going into market, ready for production. Okay. So what could be a 3D model be used for? So apart from making it your design with some features that it has to cater the function, so what kind of applications are also looking at it? Okay. So whenever you start a design, so you look at the function, okay, and then you see, okay, let's say you want to make a pen, okay, it has a cap and a holder, and now you're thinking how the cap should be fitted with the body. Should it be a snap fit? Should I screw it, or shall I just hold it by friction? Okay. So so it is not viable for you to develop all the three concepts and make a physical objects, invest in it, and then you decide which is going to be the right one for you. Okay. So 3D CAD, when you develop, so you start developing multiple concepts inside it. I will also take you through a live case study that I was able to be part of. Okay. So then to get the feel of it, you may go to a 3D printing. Okay. So 3D printing is also known as additive manufacturing. So you go for an SLS, serial lithography, FDM, fusion deposition modeling. So there are several SLA techniques. So you make a prototype of it and just have a look, And in some cases, you may also get a, let's say, a functional testing as well. So relatively, since 3D printing is not an actual representation of your production process, there is also a process called soft tooling. Okay, so you have your concept ready. So let's say of the three, some of the concepts. So yeah, prior to going to the 3D printing of this thing, let's get into simulations. So simulations, also referred to as CAE these days. I mean, it has been, it is a simulation is a subset of CAE, sorry, computer aided engineering, what we call. So simulations have been now, let's say, the most reliable, are becoming more and more reliable as more and more data is getting available. The technical specs are being developed. More R&D is done on the materials. So you have thousands of materials. So you can do structural simulations. Okay. So what should be the insertion force? Is the material is going to take up the um, forces of holding a pen, let's say, by supplier. So you can do manufacturing simulations. You may have heard about plastic injection molding, mold flow simulations, to see even though your component is meeting all the specification, but is it still manufacturable or not? Is there a problem in the molding? So you've chosen a particular kind of material. So are there any issues in the component as such? So which is reflecting the quality of the component. Okay. And from there, once you develop multiple concepts, use simulations. So simulation softwares are also now getting embedded into the 3D softwares these days. Okay. So you have an added plugins that are getting added to the 3D software, which you need to take the license for. And this can cater your, let's say, basic simulation, maybe a component level simulations in that way. Okay. Then you approach a soft tooling. Okay. And in the soft tooling, you develop your frozen concept. You also get a chance to replicate your actual production process, manufacturing process, sorry. And these components, what the simulation, you're creating a virtual environment of the test requirements, right? And now once you have the physical components from the soft tool, you go for testing. Again, you see if there are any problems. So there are some unavoidable or something that you were not able to simulate in your virtual scenario. You again do a design iteration. So design iterations means modification of a 3D model. Okay, so let's say everything is fit from a fit and function point of view. It is going to manufacturing, and let's say the operator has a difficulty while he is trying to assemble these components. He's not able to hold them, or let's say it is causing an injury to, or a pinch hazards to operators or the users. So this, again, there may be a design iteration. So you go to the go back to a 3D model. So all these stages you are able to do before you are actually investing on the your actual tools or on the actual physical. You're not going back to your drawing board once you have done all your investment. So you are actually saving a lot of time doing the iteration, and also a cost to your organization. Okay, so DFM again. So DFM implies even the manufacturers have their requirements for manufacturing. You may create a perfect parallel component or a perfect straight component, but uh, in manufacturing they will need some kind of tolerances, right? So they cannot reproduce exact, and they can be precise and accurate, but the precision levels can only be as much as your tolerances demand. Okay, so if you are going for a stricter tolerances, they may have to use a more stringent process. They have to change the process itself. So here we are regularly interacting so with them. So if there are some kind of drafts or some radii that are missing, or they want to add up, so we again interact with the 3D model. Once after so I have deliberately not tried to put the product development process here, but I wanted to concentrate more around the 3D CAD process over here. 3D CAD modeling, how what kind of impact it is making for you. Okay, so yeah, so this is how we are going for a robust design. And any questions right now at this point? Okay, so this is going to be getting a little more interesting. So what you're seeing on a screen is, let's say, is a front loading washing machine. Okay, so some typical components, what you can see. So there are two plastic parts, which we can call it an outer door and an inner door, which is, and a glass window is getting sandwiched in between. So we are particularly interested in this outer door. Okay, so let's say we are going to design this component using a 3D modeling software. Okay, and as you can see, it has an attachment. There are a number of screws, so at least 7 screws, with which both of these components are getting attached together. And also you can see some hinges, and some more intricate features what have been developed by the designer in this case. So for the screws to attach with the inner door, we have the bosses. You have annular snaps inside and outside, so which are getting also snapped. So it is also holding the outer door with the inner door, like in this fashion. And you have some more features like handle. So in this case, the handle is the user interface point. Okay, so user has to pull this to open the door. Okay, and so there are some grip patterns. So he has to get a good feel of it, and also these patterns should be manufacturable. And there are some other features like the support tabs, which are used for the glass window to rest on. Okay, the resting ribs and the supporting ribs. Okay, so here I am going to take a typical case. So there are many features that has to be engineered. Okay, this cannot be modeled. We have to be very sure that this, let's say this boss, when it is getting over tightened, should not break itself. Okay, or let's say during the period of use, since it is a very long boss, it is a slender boss. So maybe there is a jerk or in the packaging somewhere, they should not break. What would it would imply if it is going in this way to the customer, or the customer is facing issue after a certain point of time? It would give a perception of a very poor quality, right? And since nowadays plastics have taken up the entire industry, and it has to be, we may have to make sure that they are designed in the optimum way. Although the material could be superior quality, the manufacturing could be of a quality, but if it design not catering to the function it is intended for, it will be referred to as a poor quality. So yes, so what I was saying is, so this is the handle, and let's say, imagine a case, the washing machine is running now, and you know that when the front loader washing machine runs, it also self-locks itself. So during the wash cycle, you cannot open the door, right? It is positively locked with it. And there could be a case where the consumer is trying to forcefully open this handle, the door, okay? He wants to open it with a heavy force. Or it may have happened that something is stuck inside. But we want this handle to be so rigid that even with the application of force, the handle should not break. Okay, so maybe let's say we have a design limit of 200 newtons, and this handle should be able to hold without any permanent deformation or crack. Okay, so what you can see, this is a typical case of a cantilever, and it is getting merged in this portion. And as someone could also suggest that this may be a weakest portion over here, and we want this to be as strong as possible. Okay, so we have 6 screws, if you can see, 1, 2, 3, 4, 5, 6, and we have an interaction here. So the screw that is getting attached in this portion is going to take a lot of stresses compared to the additional screws. Okay, so this, please bear in mind, we are not deviating from the topic of 3D modeling. Okay, but I'm just trying to say how it is useful and what kind of design concepts we have to make before we ensure the robust design is given to the manufacturing. Okay, so I'll go forward. Any questions at this point?
No questions from audience.
Okay, yeah. Moving forward, yeah. So this is a snapshot. So please bear that this we are using only for the education purpose. Okay, so let's say this is a 3D model. this was developed, and this is the area where we are trying to develop the screw connections. So we know that this is going to get a load, a grab load from the user. So he is going to grab the handle over here, and we are going to develop some stresses in this region in the back. So that is where the screw is exactly located. Okay. So if you see, this was how this design started up. So when you see that this design has started up and the forces were being applied, and we understood that this is a very weak portion. So material, the plastic material, whatever we chose, so the forces are exceeding the strain limits of this component. So this is the load in this direction we are applying. Okay. And if you see, it is generating strains over this region. So we gradually iterated in 3D models. So we developed multiple concepts. So this is, I'm just speaking of one portion. So we generally do it for the all the functional features, whatever we should see that the function is being achieved. Okay. So we went to a doghouse kind of design. Okay. So this is the simulation, what you are seeing here. And it is also developing some strains. So we see that it may develop some cracks in this region. We went for an integrated design again. Yeah, if you see here, this is integrated over here. And finally, we made another design choice. So in which we merged the surface and we improved this boss. And this also, we were continuously we were working with our manufacturing team, if it is possible for them to create it or not. Okay. So early supplier involvement is very important, because you may end up doing a very strong design, but if it is not manufacturable, so it may be again okay. So during this process, when we are developing these concepts and doing a structural simulation, so involvement of the supplier, what you see on the right side, we also did a injection molding simulation. So this is a structural simulation and this is a manufacturing simulation. So we were seeing if the part is feeling good, is there points where there are no fillings happening? Is there a shrinkage or is there a warpage in the component? Is there shear rates that are exceeding the melt point of the plastic material? So that may result in, let's say, burn marks on the component. So this is also a aesthetic component. So this should be looking good. So there should not be visually any kind of defects. So it should also purpose the cosmetic function of it, right? So in this way we built it, and what you see here is the 3D print component. So this we wanted to, since this is a cosmetic and a user craftsmanship, user interface, UX handle is there. So we wanted to see the feel of the handle. If the ribs patterns are creating any kind of sharp edges, or is it comfortable when pulling? Okay, so these kind of features. And finally, after this confidence, this level of confidence, let's say for a particular feature, we iterated it multiple times. As you can see, it has been iterated at least 6 times in this design. And then we came out with a soft tool component. This soft tool component, or also representing the production process, that we put on the actual test rig for the final validation. Okay, so this is the lab setup in which the actual component has been placed, and it was passed in the first time after being physically produced with flying colors. So I guess you can appreciate the role of 3D modeling here, and how it is catering to different teams, right? The simulation teams need this 3D model to simulate. The prototype guy needs 3D model to make a prototype. The soft tooling guy also needs this tooling to do the injection molding analysis. So prior to getting investing on your actual tool, so we are able to reach out to a decision. So maybe not all of this could have been possible by a hand calculation, because these days, if you see, the surfaces and all are getting, they are not standard shapes. They are not a simple rectangle or a triangle where you can take the cross section, measure the moment of inertia. So since the surfaces are getting complicated, we are relying on the available tools. Okay, and that is how a market or the consumer needs are also growing, are changing actually. Okay. Any questions here?
Chaitanya, one question. Apart from part knowledge and assembly, can we do simulation in Creo also? From one of the audience.
Yes, yes. So like I was saying, so typical simulation tools popular in the industry are like ANSYS, LS-DYNA, or yeah, I mean, or there. Creo Simulate is also there. So in Creo, I will show you further on the tool as well. So the this kind of knowledge that has been developed by the CAE companies, the software industry, they have added plugins that can interact with the 3D softwares. Okay, so to answer your question, it is possible. The simulation is there inside. It requires a different licensing, but it is also included in the basic pack. Okay, so what they have done is they have made these softwares that so that they can speak with each other. Okay, so they have given us some basic features of the simulation that you can do directly in your 3D modeling environment. Especially in Creo, it is possible. You name any 3D modeling software, it is possible. These days, simulation is possible.
That's it. One question.
Okay. So next slide speaks of how a typical parametric 3D modeling software looks like, the process, what we do inside. So we are again going back to our topic of 3D modeling. Okay. So generally you have a 2D sketch in the start. Okay. And this sketch gets extruded. So the sketch, you can add a thickness and grow it in a specific dimension. You can revolve it, you can make cut features. So according to the need of the design. So the 3D part is coming up. And this 3D part, you can check your interfaces in your assembly. In this case, the component is self assembling with itself. Okay. So it is a stack of battery holders. Okay. And finally, you also do a 2D drawing, so which captures the tolerances that are included on the component, right? So these tolerances, let's say, can be what you discuss with the supplier and what actually your function is needed for. So bear in mind the manufacturing processes. If you're doing for a mass production, the tolerances will have their own limitation. So yeah, and if you're looking for a very precise or a let's say 0.005, this kind of tolerances, 0.001, then the production quantity may be limited because you may have to adapt for a very more sophisticated manufacturing processes. Okay. Yeah, so I will go to the next topic. So this now in the next thing, I will be
Chaitanya, one question from the audience.
yes.
Sir, why not drawing in the beginning itself?
Okay, so so drawing is something that has to okay. So draw. This is a typical thing what was happening in the past, right? So let's say. Okay, right now the 3D modeling software, how it works is from the you are able to generate your views from the 3D model itself. Okay, in the past when there was no support of a 3D modeling software, even like you recall in the engineering first year, we use in the engineering drawings. So we are going to this drawing hall and using a drafter. So typically we are looking at some model and just we are trying to redraw it. So we are trying to learn what the basics are. So anything that is in this real world actually was a 3D object, right? And if you want to design something and you want to see the functionality of it, so you have to build this model. And whatever app, so drawing is basically a representation of 3D models, and more specifically, you are just speaking of the core areas that you are interested in. Okay, drawing may not be so especially for complicated objects, like let's say you have a 3D surfaces. Maybe you can take an example of an automobile, Altos. So it is so the surfacing is so well defined. Are we able to represent everything on the 2D drawing? No, right? But what the drawing will carry the information where this, let's say, the bonnet or the is going to interact, the screwing points. So those will be very closely toleranced. So drawings will be majorly concentrating on what suppliers have to or take care of, so that the fit and function is maintained. Okay, so we may be able to do, but let's say in that if we are directly reaching to a state of where we can start with 2D drawing, in that case maybe a 3D model is also not needed. So especially for civil applications, so in AutoCAD application, so we more popular for the 2D itself because it is a plan view. So you know that let's say a floor plan, it is going to get extruded in floor by floor in that order. So in those cases, you don't totally need a 3D at all. Okay. Yeah, does that answer my question? Your question?
Chaitanya, one more question from one more audience.
Mm-hmm.
Sir, in case of alloys, how we have to add material properties, for example, like aluminum with silicon carbide?
Good question. I will give a small, so let's say, see, this is a typical component. I may have not yet added a property. So believe me, there are now lakhs of material compositions that are available or to choose from. Okay, so the model, every alloy, if you are speaking of a metal, so it is associated with a standard, AISI or an DIN standard. Okay, if you are speaking of a plastic, then the supplier will have their own technical data sheet. Okay, if you see, this material right now is not assigned, and by default you will get some list of components in the library. Okay, so our friend was asking about an aluminum. Okay, so we have two grades of aluminum here. Either we can choose from these two if it is sufficing our need, or since you are speaking of a specific alloy that has a property, okay, you can also create your own new material and assign the properties from your technical data sheet. Okay, so the density, the Young's modulus, the thermal properties, the hardness, okay, miscellaneous like bend factors and the hardness. So these all can be defined, and this can be saved to your library and also applied to your model. Let's say in this case, I know that this is a plastic part. Let's say I give it as a nylon. So you see, nylon, its density. So right now the units are coming in terms of pounds. We may want to switch it over to mmks, metric system. Okay. Yeah. So it is possible. So whenever there is not a material, so you generally seek the material data sheet from the supplier, or you look at the standard, and those properties you are able to create or replicate in your 3D modeling environment.
Thank you, Chaitanya.
Yeah. Any other questions?
No, Chaitanya, that's it.
Okay. So this is where it is going to get boring now in the session. Okay. So I am trying to replicate what are the elements that are involved in a 3D model software. So I understand part of the reason for this session is also to make aware of the audience what kind of tools are available in the field. Okay, so this is not a software specific thing that I'm going to tell you right now. It is almost the environments may the aesthetic or the visualization or the UX may differ, but the elements still remain the same. So somewhere some options are coming forward, some are going back, but the language what you speak is will remain always the same. Okay. So before we start a 3D modeling software, okay, so when you say file new, so you get this kind of options. So let's say on the left side, this is how it looks like in Creo, And this is how it looks like in Autodesk Inventor. Okay, so you can create a part, an assembly, or like someone said, we can also directly start with the drawing. So in the drawing, you can directly use the sketches and start making the views and projecting it to, and start projecting the side views or the front views, depending on the need. Okay. So, and typically extensions, what kind of extensions are there? So we have for a part, we have a .prt for an assembly level. So what is a part? So this is a geometry of individual part. Okay. So we can also create a sheet metal part or a part model at this point on many of the 3D engineering 3D parametric softwares. Next is an assembly, which is .asm kind. So typically this is an assembly of one or more parts. Okay. In fact, it is a link of one or more parts. Next, you can see drawing. So drawing can exist in a .dirw, DWG, DXF files. So the files created in the design environment have this extension. Okay. And last, what you are seeing is, so let's say you are coming from, you're trying to develop some component which uses screws and also you need some standard screws and nuts or bolts. Okay, so these are standard components that are already available in the market. You can just pick them off the shelf. So supplier, along with data sheets, these days we can also directly download 3D models from them. So he as an individual has to cater all the industries irrespective of what kind of 3D modeling software we are using at our organization level or at your organization level. Okay, so you have this formats .stp, IGS. Okay, so these are directly downloadable into your 3D software. Okay, so you can import this geometry directly into your 3D softwares. And I also know that the industry is working, let's say, a Creo to SolidWorks. You want to transfer a model. Okay, so what I do, the model, what I have done in Creo, I export it as a STP file or a IGS file and share it with the colleague who is using the other software. And these days they are also developing this kind of interaction where they can directly use the core file, that .prt file, they can directly import into the other environment, the other 3D engineering software. Okay. And the other main role of this STP IGS is, so whenever you have to give it for the tooling or machining, or you want to do a CNC operations, so your manufacturing team will be asking the step format of it. The suppliers will be asking to give them the step format so that they can import it into their controllers or onto the CNC machines. And also 3D printing. So STL is a very commonly used or a specific standard, and is a lithography this thing. So this uses converts the model into layers of components, so which can be used for the 3D printing or the additive manufacturing, advanced manufacturing. Okay. So any questions here?
Chaitanya, one question from one of the audience, from Subhash. How to design the porous materials like human bone?
Okay. Good question. So I know I have a experience with porous components. Generally, they are called sintered components. Okay, wherein the dense. So on the 3D itself, we are not. We are going to assign the density itself. Okay, so we because it is just a 3D representation of the actual form or features. So the density is what is going to play a major role there. Okay, and coming to the porous aspect, this is also getting popular in the additive manufacturing. So also you are able to, you do a normal modeling and assign it density. So whenever, if you are going for a 3D printing models, so the conversion software has a inbuilt facility that it can also make the components hollow or porous, and it can build in layers in that format. So as such, in not, if you want to go that way, so let's imagine a bone. So maybe you have to start with slices by slices, but that may not you may address the same issue by first building as a normal 3D model, assigning the density of the bone, okay, and then developing it in, exporting it to into a software where you can impound this kind of properties, like let's say the porous or this kind. But yeah, good question.
That's it. Only one question.
Okay. So going forward, and yes, this I want to also fetch you a fair representation of the software whenever you open how it looks like. So this is particularly the Creo environment, but the options may go from here and there when you are using softwares like CATIA, SolidWorks, Solid Edge, Inventor in that case. Okay, so you always have a graphics toolbar wherein you are going to have the 3D model. You have a model tree which is capturing the feature histories. You have the toolbars and different tools. So these I'm going to just cover in the upcoming slides. So design environment. So design environment, what you can see here on the left, we have a Creo design environment, and the right we have the Inventor environment. Okay, so what it will have is all 3D programs, they have a similar design environment. So it allows you to view, edit, or document, okay, your CAD files. So it also, the 3D model itself, like I said, it will sit in the center of the environment, and the tools what you want to use to manipulate the files. Let's say you want to add a radius, you want to add a chamfer, you want to cut. So they are all located on this window itself. So again, when you are using a different program, so the tools may be in different places, but we will go through the most common tools on the demo. Okay. Next is the viewing tab. Okay, so typically also in Creo it is called a graphic toolbar. Okay, and it has the commands for you to, it allows you to zoom in the model, rotate the model, or change or the view of the model. You want to orient it in a specific view, say front view, side view. So those all things are possible here. Okay, so you can also switch the edges, you can render the model, you can hide the solid and only see the wireframe or the edges of the component. And you can also at the same time switch on the axis, coordinate systems, planes. And so regarding this, I'm just going to take forward because this is also an important aspect to understand a 3D model software. Next is the feature tree. Okay, so here it is also called as a model tree. So what you see is it displays all the types of operations in the sequential order in which they were built. Okay, so if you see this very simple model, so I have created let's say 5 features. Okay, so the first feature, it is catering to the top plane, the yellow portion. The second, it is catering to the right plane, the green one. And the third, it is creating to the front plane, okay, the pink one. So it comes, so these 3 planes are actually forming your 3D space. And okay, and I will just take it a little further in this one. Yeah, this is also a bit interesting. So carrying on the same discussion, so we also have what are something called as planes, axes, and points. Okay, so planes, maybe it is a bit clear from this model. So we have 3 planes, and with the help of in these 3 planes, a 3D object can be defined. Okay, so and you have the axis where the 2 planes are getting intersected. So you get the x-axis, z-axis, and y-axis, and where these 3 datum planes intersect each other, we have the origin point. Okay, so since because this is an important piece of a 3D software, because we use these planes, points, and axes as reference geometries. Okay, so yeah, you can locate your part and features with these planes in the 3D space. Let's say, because so this is forms the 000 of your component. So of your component. Uh, so the CAD programs, we are working in a Cartesian coordinate system. So any component or any surface or edge, we can represent using a 0, 0, 0, the location of this line or point with respect of X, Y, and Z, right? So it is, and also the reference geometries, whatever we are going to create, can be, we use them for sketches and also features when designing the part. Okay. Any questions here? This is actually the base of any 3D modeling software. So it is important for us to understand what is a front plane, a right plane, and a top plane. Okay.
Chaitanya, one small question. It's not relevant to the following topic, but any free software for designing porous materials for biomechanic applications?
I'm not aware at this point if there is any software that may be available, but I'm not aware. Me particularly coming from currently catering to the healthcare industry, we are using Creo and Solid Edge.
Thank you, Chaitanya.
Okay. So next, I wanted to take through the basic sketches and shapes. Okay. So many of the time, the CAD programs will itself have some built-in basic shapes or sketches that are built inside the software. So you can either extrude them. So these sketches can be built with thickness to make a 3D model, or you can directly call them in as 3D shapes also. Maybe a standard shape of sphere, a cylinder, a block, this kind of thing. Okay. So since I'm going to show the basic functionality of the 3D CAD software so that you can get started. So some programs will be different from others. So Unigraphics has a built-in solid blocks also, 3D solid blocks. And while if you see in Creo, you have this line, rectangle, arcs, ellipse, some basic features, and also a template wherein you can pick some standard shapes and you can use them directly. So next is, so we also want to understand what is a part, what is an assembly, and because what is possible in a part environment. So this is also a common thing across all the 3D modeling softwares. So a part file basically is the basic component of the 3D software. It represents single component or pieces, and it can be a part of a larger assembly. Okay. So when designing a part, we can use a wide range of 2D sketching utilities or some kind of forming tools. Okay. And in the modeling software, and get the desired shape what you want. Okay. So for example, the battery holder in the image what I'm showing here is, it has a variety of extrusions, cutting features. Okay. Cutting features, holes, and chamfers, and radius features. Okay. So among other things. So both have actually started with simple shapes. So maybe I have started with a simple circle and a rectangle, and step by step as it matured, we had this finished part in this format, the final design. And this design is also used by the manufacturer, so he can obtain the information of the part, including dimensions, what kind of tolerances, the materials, and even if you wanted to have this component painted, so if the material is feasible, or is there any intricate shape where the painting is not possible. So that kind of information the manufacturing is able to now confidently give us a feedback. Questions here? Okay.
No questions yet, until now.
Yeah, assemblies. So like I said, assemblies are 3D files that contain multiple number of components or parts. Okay. So in assemblies, you can connect parts together with the different, so there are many constraints that are available. Okay. So you can make it a coaxial, coincident, parallel, radial. So there are several options. So you want to just leave it in a specific orientation. So the features still remain the common across all the 3D softwares in a 3D modeling software. Yeah, I think that was the small snapshot what I had to share. I know the session was supposed to be until 11. Okay, so maybe I have wrapped up a little bit early at this point. So I will open the floor for further questions.
Participants, any questions, you can ask it in this question and answer window, or you can raise the hand so I can unmute you.
Okay, so since we have some time left, can we also take a small demo?
Sure, Chaitanya. Yeah.
Okay, so I had actually reserved two components that I thought maybe we can use for a later if the time permits. Okay, so let's take this part. Okay, let's say, so there are basically two parts. So have 1 and 2. Let's see if the time permits. I will quickly show you a demo, and please keep it open if you have any questions. So I'm going to follow this 3D model, okay, and how we can build this, okay. So let's get into, let me close all the files so that I can show you. Yeah, so this is how a typical Creo window looks like when you launch it, okay. So what you want to actually do it, you also want, before starting a project or you design by yourself, it's a good practice to set a working directory so that all your components are getting saved to the same folder rather than scattering here and there. Let me name it exercise 1. Okay, and I set it there. So whatever, so this is a new, just like, so imagine it as an advanced version of an MS Excel or an MS PowerPoint. So these are, so new, so we want to do the part, okay. Let's say it as a block. You can give some more description of it. Block lower, say remove the template. So I will use the metrics standard. So MMNS part solid. Okay. And yes, here we go. So okay. So what you're seeing here is a block with a solid block, and in which there are several cuts. Okay. So either you can start building. It is up to the approach of the designer. Okay. So if he knows that there is a standard block available in the market, okay, maybe he can already start building up first with the actual block shape and then start removing it. So okay, so let's say he knows that he there is a 62 by 65 block already available in the market, okay, so which the supplier is going to use to machine it. So it is also a good approach that we first build the block and then do the machining or simulate the manufacturing process. Okay, so let me try first building up this 62 by 65 block. So I select sketch, okay, and I have selected the top plane, okay, and So if you see this, we have this as 62 by 65. I will also try to turn off. Okay, so yeah, so this is a 62 by 65 thing, and now I have to also move it, extrude it in this direction by 40 mm. Okay, so this is how typically your sketcher window will look like. Okay, so this is your top plane, and once I am out of it, and now I select an extrude. Okay, so it is asking me how much I should extrude it. Know that it is a 40 mm. Okay, so this is good and this is good, right? Okay, 40. Yes. So next, what we know is, so there is a this cut feature over here, okay, which is getting removed on both from both sides. Okay, so yeah, so this is a 50 mm cut. And before that, we also see that there is a 12 by 38, that is this window, okay, which is in where there is no material at all, and it is symmetric against both sides. 40. Maybe we can take up this. Huh? I will take this window. I will use an extrude. So this is 40. I'll give it as a center line. I will again take a rectangle that is symmetric around this axis. Okay. Suppose this was not symmetric. So there are many constraint tools. I can again demonstrate that. So let me say I have made it in this format. Okay. But I want this feature, this rectangle sketch feature, to be symmetric along this center axis. So we have constraint tools, which are also again very common across all 3D modeling softwares. And here you go. And I have made it as a symmetric. Now we need to get the dimensions. It is 12 by 38. So I think it is 12, 38. So now it is actually showing me that it is adding material. So what we want to remove material, and it has to be in the opposite direction. Okay. So I remove it in the opposite direction. It is asking me the depth of it. Okay. So maybe I can, so again, we have several options. So is it symmetrically, you want to extend it to a certain surface, you want to extrude through all to whatever is coming outside. Okay, so maybe I can select extrude through all. Okay, so it is giving me this cutout over here. Okay. Next, so this is also done. So now we have this T slot. Okay. Now we are interested in this particular T slot. So which is 40 by 25 width-wise cut, and we have total depth of 20 by 8. So I select this feature. So this is where it is. And again, use an extrude command. So you see it is already auto snapping onto the lines. So just in case you don't want it to auto snap and you want to define it, you can go to references and you can select those edges that you want to pick as a reference to your newly created geometry. Okay, and from here I'll start creating the T slot. So again, if you see, so firstly, to have it symmetric across an axis, we may have to create a center line. That is what I'm creating right now. And next, I will mark this symmetric along this line. Okay, I will also take this and make it symmetric. So yes, it is saying it is a redundant dimension. So since, okay, so it is already self this thing. So this understood is 40. We define this, this is 20. Let's go back to the drawing. 40 by 25. Okay. And this is 20 by 8. This is 8. And this is 20. Okay. So now again we want to remove the material. So if you see, as soon as I switch the direction, it started removing it. So but now in this case we want the removal of material only until a certain point. Okay. Maybe I have, so if you see, this length also was a little, is not 62, it is actually 50. So we may also want to remove this material over here that is getting extended right now in our component. Okay, let us also consider that. So that is 50. Okay, so let's say and now I will use the delete. Okay, it will delete this portion. And you see, as soon as it is forming a closed loop, it also highlights itself as a closed loop. Okay, an orange translucent surface. So we want this to be ideally 50. Okay, yes, 50 or 50, yeah, 50. Okay, so this is 50, 28, 25, 40. 50, 28, 25, 40, right? Okay, so again it is asking us up to what surface. So this time we have the option also to up to a selected surface. Okay, so I will take it and I will say extrude until this surface. Okay, and if you see, until that particular surface we were able to cut. I think there has been some mistake. 38. Okay, let's go back to the drawing board. I believe I think we may be good there. So this is a coincident. I want this point to be coincident with this to be coincident with this. Okay. Yeah. So it would appear that the length is fully covered. Okay. And next, let us take out this portion, this small rectangle portion from here, and that would suffice our component. 38. Okay, my bad. I have made a mistake here. So after this extrude, we want to remove this portion of material. Okay. So this 8 mm material we want to remove from here. So this is standing at 50 and this is 25. Say remove, I say through all. Okay. Yes, this is good. And then I go for the extrude. So this extrude. So I can also change the references. Okay, so I change and replace it with this surface so that the section is moved a little back. And at the same time, since this is a throughout section, okay, we can also extend it. Okay. So next we are coming to this. So before coming to this feature, we also want to remove this edge over here on the top. Okay, I will use a constraint to put this point on this vertical line. Yeah, you see it has taken up, but still we want to select it to the respective surface. Yes. And here we want to replace this surface with this gun here. Okay. Yeah, there we go. So this is the 3D model what we are able to build. Okay. So here if you see we have majorly used one common command, that is extrude. Okay. So I think the entire features we were able to build with extrude command. Okay. So this is and we also were able to remove material with the same command. Okay. This is a very commonly used tool across all the 3D platforms. Okay. So for making a T-slot or this thing. So any questions here? So I'll keep it in the default state and
Chaitanya, two questions are there. How to
yes.
simulate a player and his tennis racket for my AR game? What is the software that can be used for this task?
Okay, so AR definitely it is not my cup of tea there. Okay, and I almost forgot my tea. So I maybe I cannot help there, but mechanisms or animations that is possible in your 3D software. Okay.
And the
Let's say
second
you
question,
want to.
yeah, continue.
So let's say you have a mechanism, a gear mechanism that a planetary set of gears. So you have a drive shaft and it is driving a set of gears. Okay. So those kind of animations you're able to do in the 3D modeling software, your engineering parts. But if you're speaking about a very, let's say in this case, a tennis racket for a game, then maybe you have to rely on the animation software. Like I said, we are concentrating this session for the 3D modeling softwares and not on the animation aspect. And AR, we are frankly, I mean, I'm not the right guy to speak with.
Chaitanya, second question. Sir, we are planning to use Blender or SketchUp for teaching AR VR applications to our students. it is a wise choice. I have never heard that Creo before. Means is there any relation between Creo and AR/VR?
I know that PTC is coming up with AR and VR tools recently. Okay, so that is a separate set of tools apart from Creo. So here we wanted to see the. So let me go back there to the slides. Yeah. So again, sorry. So my field of experience totally lies with the 3D modeling softwares. So for any AR or VR platform application, I can definitely say that Creo may not be the right tool at this point. Okay, because Creo we are majorly relying for engineering parametric 3D models. That is, it's one of the strong point. Okay, so I also learned that you had a session on from PTC for the AR and VR. So I think those colleagues can point you in the better direction for this application, AR VR application.
Chaitanya, one more question. Once they do this 3D modeling, can they superimpose on like a 2D image or a 3D image later on?
Yes, definitely.
Something like a virtual, right? If they superimpose on the image that they want to display.
Yeah, I can actually give you a very good example. We were using in general models. Okay, so what used to happen was, so there was a team itself which we used to call measuring point systems. Okay, so the 3D model is the theoretically exact representation of what the designer wants, right? So it is representing virtually the exact 100% accurate model. But once the components that are manufactured, let's say a stamped or a sheet metal component, which is done in a press, so it is coming out. And now there are two ways. Either you can measure it the conventional way, and there is the height. But let's say it is a very complicated shape or a 3D surface. Okay. So what they do is they scan this component and they generate a cloud of points. Okay. So this cloud of points is transferred into the 3D model software, or you can directly import it as just like a step file or something. And then in a simple assembly, you can superimpose your 3D model and this cloud of points. And you will know exactly where the component is meeting the dimensions, where it is deviating, where there is a spring back, where there is a, let's say, out of custom line. So these things are quite common in the industry. Yeah? So this is, again, the raster scanning things. If you guys had a chance to visit IMTEX in Bangalore, which is held yearly in BAEC, Bangalore International Exhibition Center. So yearly they showcase many kinds of advanced technologies that are popular in the industry. So they are able to scan a human body. They can bring it into the live environment of a 3D modeling software. Okay, it can be a car they want to reverse engineer. They can scan the components and again bring it back. They want to do an inspection. They can scan the actual component and superimpose the model onto the actual 3D part.
Thank you, Chaitanya. Any other questions from the participants?
I think we can wait. Huh? So I would appreciate if the session is made in this format itself. If people are getting more questions.
I think that's it, Chaitanya, and we'll meet again at 11:30 for the session 2. All the participants are hereby requested to join like 2 minutes before the session, so we can start exactly at 11:30.
Okay.
Thank you. Thank you, Chaitanya.
Okay. Yeah. So just to give you a glance, so this is what we are going to do in the next session. So we are going to create a C-clamp, design the part. I mean, we already have the parts developed drawings. So we are going to do an assembly of this. So just for the interest of the participants. Okay, then I will sign off for the while and see you guys back at 11:30. Yeah.
Thank you, Chaitanya.
Participant, please fill the feedback form for the session 1.